Welcome back. In this lecture, we're going to look at the size of the crystals in a mineral depending upon how fast it cools. You're going to see that the faster it cools, the smaller the mineral sizes are because it didn't have the time to grow big. So the longer that a mineral can form, the bigger the crystal size. So if it cools down very slowly, you're going to have large crystals. If it cools down very quickly, you're going to have small crystals. And then if it cools instantly, you might not even have time for crystals to grow at all, and you would have something like glass. Another possibility of texture will be the presence of air bubbles, and you have a vesicular type of a texture where that it cooled off so quickly that the air was trapped inside the lava as it was cooling down, and it ends up freezing those air bubbles or gas bubbles or water bubbles, whatever they are. Okay, so when you slowly cool a rock, okay, so let's say something was in a magma chamber and it never actually reached the surface of the earth and cooled down very, very slowly, or something extruded and went out of a volcano and went into the air really, really fast and cooled down quickly, or it went into the ocean. So you can have an underwater volcano and it went into the cold seawater and it cooled down really quickly, or even the case of, say, a volcano underneath a glacier and that ice would cool it down very, very fast. You're going to have different size grains of your crystals. The crystals are going to cool down and form. So the crystals, there's no crystals when it's melted. You only see the crystal when it's solid. So when it cools down into a solid again, you'll see the crystal. So a lot of times the size of the crystals have to do with how they cool down. So could you write this, please? Large crystals indicate slow cooling. So anything that's plutonic or intrusive, something that's underneath the ground, is going to slow down, is going to slowly cool down, and it gives time for those crystals to get really, really large. Okay, so if it cools down very fast, it didn't give time for those crystals to become large, and so the crystals are very small. So really, really tiny crystal rocks suggest that if they were igneous, that they cool down quickly. Large crystals in your rocks will indicate that they cool down very slowly, and so that's the idea. If you've got large crystals in a rock, it most likely formed very deep under the crust, and then because of that, slowly cooled down, giving lots and lots of time for the crystals to grow very big. Conversely, if you have small-grained crystals, okay, small-grained crystals is an indicator that they cooled off quickly, okay, maybe not as quick as you could, but quicker. So the smaller the crystal's size inside the rocks, so some crystals you can only see with a microscope. You can't look at it with your eyes and see the crystals. Others, okay, so a lot of you are familiar with granite. Granite, you can see the black and the brown and the white very easily with your eyes. In fact, that's the reason why you would buy that stone to turn it into a countertop, is because you can see it. It's pretty, okay? Granites are very deep down rocks, and they cool off very, very slowly, and that's why the crystals are big. If you have very fine-grained rocks, then either they came out of the volcano and you have an extrusive rock, or they cooled off rather quickly. They were near the surface and they were very quick to cool, okay? So the individual crystals sometimes you can't even see. They're too small. You would need actually a microscope to see the crystals, okay? Then if you have vesicular texture, remember a vesicle is like an air bubble, so it looks like bread on the inside. So if you have a vesicular texture, it means that there was gas bubbles, and those gas bubbles were inside the magma or inside the lava, and then when they cooled off, there wasn't enough time for the gas to actually percolate out of the rock. It stayed in the rock and basically made a void. So essentially it's a frozen air bubble or a gas bubble that remained whenever the lava solidified. You're going to see that vesicular texture is very common with lava rocks, so extrusive rocks, because it came out so fast and cooled so fast that it didn't even have time for the gases to escape the rock. It froze the gas bubble in time, especially, and then you have this spongy looking rock. So pumice and scoria, these type of volcanic rocks have bubbles in them. Okay, so a review. Coarse grain texture, okay, solidified at depth. Okay, so it slowly cooled off, and you're going to have large enough crystals that you can see those crystals just with your eyes. You don't need a microscope. Okay. All right, the next one is porphyritic texture, and porphyrous actually does have to do with fire as well. So these are igneous types of rocks, and the crystals are large inside smaller crystals of matrix. So essentially you've got different minerals with different sizes inside the same rock. Remember, a rock is simply two or more minerals shoved together. And in the case of melted rock, they're all melted there beside each other, and then as they cool, they form crystals. Well, some of these crystal shapes are going to be large crystals and other smaller crystals. So the small crystals would have come out faster. Okay, they were able to come out faster, and then certain minerals had to come out slower. So that's where you had this porphyritic. You've got different size crystals inside the same rock. You can see, say, black specks and white specks, and the white specks are bigger and the black specks are smaller. Okay, that's what a porphyritic. It looks like something is speckled, okay, inside the rock. If you were to bust the rock up, you would see spots in the rock where you have larger crystals and then smaller crystals embedded in it. In the case that something cools down almost immediately, it doesn't even form crystals. It forms glass, especially if you're talking about silica. And most of the time, silica is the main component of lava. So silica, remember, is silicon and oxygen covalently bonded together. And in the case of glass, glass is the same stuff as quartz. But glass doesn't have an orderly structure. It doesn't have a shape. It's all melted together and just cooled in a sheet. And so if you cool a silica lava very, very fast, like something squirts out of the top of a volcano and just spurts in the air, it'll cool off instantly, and you end up with volcanic glass. I believe volcanic glass, there's several different kinds, but the one most people are familiar with is Obsidian, which is a black, very black, shiny volcanic glass. All right, so let's look at this. Here's the first example. It comes out of the volcano and quickly cools. And you get, in this case, obsidian, which is natural glass. Remember, you can see that there's no air bubbles in it, so there wasn't a lot of gas here. But because it forms this glass, it means that there's no crystal shape. The second one we looked at was porphyritic. And porphyritic is these spots where you get large crystals growing slowly and the small crystals coming out quickly. So they may be within months or years different of coming out, depending on how cool one crystal is able to come out and how fast the other crystal comes out. One might have more time to cool and less time for the other. And so you have two distinctly sized crystals, a big one and a little one next to each other. Okay. Coarse, anything you can see with your eyes, means that it's going to cool down way deep underground. Okay, so it cools down very slowly and you get coarse grained. Fine grained is minerals you can't see with your eyes. You could see these minerals. They do look like that there's dark and light in the same rock, but they're so little that you couldn't make them out with your eye. You'd have to use a microscope to see it. And you can see that this is going to cool off faster than a coarse-grained rock. And then anything with vesicular structure is going to have gases in that lava that it cools so fast that the gas didn't have time to escape, and it basically seals that gas bubble inside the rock.